Hello gentlemen, welcome to our video on section 10.6 entitled Gas Mixtures and Partial Pressures. Now, thus far we've been considering gases kind of in their pure states, just solo gases, looking at only one substance. But in reality, in nature, many gases are in mixtures, like for example air. Air is a mixture of a bunch of different gases together. So when we study gaseous mixtures, one thing to really look at is their pressure as a whole. So to do that, we can look at John Dalton's law of partial pressure, which says that the total pressure of a mixture of gases equals the sum of the pressures that each gas would exert if it were present alone. So here is a really simple equation, right? If total pressure of the gaseous mixture equals the pressure of gas 1, pressure of gas 2, pressure of gas 3, all added together. Now we can take this one step further and remember that gas number 1, its pressure is equivalent to, the pressure from the ideal gas law, which says, in RT over V if I, rearrange everything, the Pivnert equation. The only thing here that really is special for gas number 1 is how much of gas number 1 is present. Because RT and V are constant. If this is a gaseous mixture, it's in the same container. All the gases are in the same container, so volume is constant. They're all in the same atmosphere, pretty much, or condition, so temperature is constant, and R is a constant. So only thing that really matters or changes here is N. So you could do this, like that's P1 plus P2 would be N sub 2 RT over V plus P3 . So all that really changes here is the number of moles from each gas or of each gas. They could be different from one another. Okay, so each gas we can treat it independently. They all behave independently than the others or from the others. So since RT and V, they all remain constant throughout this, then you can really look at total pressure as taking the total number of moles. So moles of gas 1, moles of gas 2, moles of gas 3, add them all up, get total moles, and multiply that times RT over V. And that can get you total pressure, since N is changing or moles are changing from gas to gas, but nothing else is. Okay, so now a different scenario where we're actually a gaseous mixture through some chemical process is here, collecting gases over water. So in some experiments, gas is collected over water just because it will be hard to capture that gas just, in any other way. It's more efficient to do it this way at times. So here's an example. This is from your book in page 401. Here, we have a substance, KClO3, being heated, and it's going to decompose. Here's the chemical equation to the right. So we have KClO3 decomposing into KCl and O2. All we really care about is the gas. So we care that O2 is being produced. Okay? And it's going to be produced, and once it is produced, it's going to go through this tube and be collected right in that space. Now, as it's being collected, it's going to start taking up space. And as it takes up space, it's going to actually push down this water. And it's going to keep pushing and pushing and pushing as it's collected in that space until the water levels from the inside and the water level on the outside are equal. And once the level of water inside the beaker and outside the beaker are the same, once they're equal, that means the pressure inside the beaker is equal to the pressure outside of the beaker. And we know the pressure outside of the beaker is atmospheric pressure. So the pressure inside the beaker is now the atmospheric pressure, whatever that is. It could be the standard atmospheric pressure, or it could be some different atmospheric pressure. Now, really important thing here is that the gas inside the beaker is not just O2. It's a combination of the O2, which is the gas produced, and water vapor. One thing to know about standing bodies of water is that above any standing body of water, there is water vapor. So when water is heated to, a certain temperature, it will release some water molecules in the form of vapor. You may have seen something like this if you had a water bottle, let's say a half, consumed water bottle, and you left it out for a while. When you come back, it may have condensation on the sides of the bottle, up in the empty space where the air is. And that's because there was once water vapor there and it then condensed on the sides. So there's water vapor above every body of water. And that's true inside the beaker. So right here, where that O2 is being collected, there's also water vapor. So we find the pressure of just the gas we produce by looking at the pressure of the water vapor as well. So the pressure of the water vapor must be subtracted from the total pressure of the gas, which is atmospheric pressure, which is equivalent to atmospheric pressure, I should say. So if we write this down, the total pressure is based on the pressure of the gas that we collected, in this case it's O2, plus the pressure of H2O vapor. Now we can figure this out by looking at Appendix B. So this is not something you have to know or calculate. You look this up, or it's going to be given in a problem. And this is, the pressure of H2O vapor at, various temperatures. So depending on the temperature of, the conditions in the problem, you would find that temperature in Appendix B, and then find the corresponding pressure of water vapor, and then just plug that in here so you can solve for either the pressure of the gas or P total, but mostly you're going to be solving for this, pressure of the gas. Okay, gentlemen, this is gaseous mixtures and collecting gases over water. Take notes. We'll do some practice with both of these concepts next class. Adios.